So good afternoon to you all. Welcome to this session. In this session, I'll be basically discussing on uh, how geospatial technology can be utilized for forest biomass assessment. Now, to start with, we know that forests sequester a huge amount of carbon, and thus it helps maintaining the atmospheric carbon balance. Uh, Hence, the quantification of carbon fluxes and stock is very much essential for a better understanding of the global carbon cycle. And in this, remote sensing plays a very important role in quantifying the carbon stocks. So this discussion or this lecture is basically about how remote sensing data can be utilized for, of course, it is integration with the field data can be utilized for forest biomass carbon assessment. Now, to start with, we know that if you talk of forest carbon pools, now, so they are now accumulated in 5 pools mainly: live above ground biomass, live below ground biomass, dead wood, litter, and soil organic matter. So in this lecture, I will be discussing about the soil organic carbon or soil organic matter. My main focus is mainly on the above ground biomass, and or we can say tree biomass. In some of the case studies, I will show the combination of trees, herbs, and shrubs biomass as well. And we know that the factors which influence the amount and the proportion of carbon in each of these pools are the age of the forest and the species composition. So with age, with the different age, the biomass will vary, and or the biomass will vary in different age forests. Biomass will vary in different forest types, and in a natural forest, due to natural disturbances or maybe human disturbances, the biomass or the carbon proportion also will vary, and it will also vary with the soil characteristics. Now, this is what I'll be basically talking about in this lecture. When you talk of forest biomass and carbon assessment using remote sensing data, basically what we do, we integrate remote field inventory data with the remote sensing data derived variables for forest biomass assessment. And for doing that, there are different ways or different approaches rather. So here I'll be discussing about how medium resolution optical satellite data can be utilized, how very high resolution satellite data can be utilized, how active remote sensing data like lidar can be utilized for this kind of study, and how integration of multi-sensor data can be utilized for forest biomass and carbon assessment. So if you see the overall methodology, if you see simply, what we do is we take satellite data and we derive different variables. It could be spectral variables, it could be texture variables, and then if the forest is, let's say, heterogeneous forest, not a mixed forest kind of, so we need to stratify the forest. So for this, for stratification, we generally map the forest type and density and make homogeneous strata. In this homogeneous strata, basically we go for stratified random sampling and we do field inventory. From the field inventory, we calculate the above ground biomass. So we have one component is satellite data here. Now, if you see here, one component is satellite data. This part is satellite data, yet variables. This part you can say the field combination, field data, and then these two things are combined in various modeling approaches to map the spatial distribution of biomass. So basically, there are two components: satellite data, field data, and we are integrating this with different modeling approaches. These modeling approaches will vary. That I'll be speaking. Satellite data also will vary. Okay. And then using this, integrating this, we map the spatial distribution of biomass. Now, integration, the modeling approach, this process, this will vary from here in the modeling whatever integration process here. So here, first of all, I'll show you how simple linear regression, an example of, let's say, simple linear regression. Now in this example, if you look at this thing, these are satellite data. Here we have used IIRS P6 and Cartosat PAN data and merged this data. Okay, Ultimately, what we are getting is the forest type density. Why we are making this or generating this map is we need to stratify the forest for collecting the field samples or ultimately to get the biomass of this area, field biomass. And from the satellite data, what we are taking, that in this case only one variable, that is NDVI, we are taking in this case, and then we are going for regression modeling. In this case is simple linear regression. Now in this case, we are assume that NDVI has a relationship with woody biomass. So here we are taking only one variable NDVI, and then we are relating it to woody biomass. And here in this case, woody biomass is the dependent variable and NDVI is the independent variable, and we are going for simple linear regression. Now we are considering this is the standard FCC, and here we have done the this is the vegetation type, or you can say forest type density map. What we are talking of here, this is required to stratify the forest, and then we lay sample plots to calculate the woody biomass of this region, of any region. Now this is the area estimates under different type density classes. Now the question comes, first of all, like when we are going for this kind of study, now how many number of sample plots are for field data collection, how many sample plots are optimum to study this area, of forest biomass in this area. And if we calculate the number of sample plots, let us say 30 or 35, second question comes, where to lay these plots. So in this case, stratified random sampling. So first of all, we do a pilot survey. In this pilot survey, what we collect data from the field, and using this Charcos formula, we calculate using this formula, we calculate the number of sample plots, or you can say optimum number of sample plots required to study. Now here n is equal to t square multiplied by cv square. Now divided by ac square. Now cv is the coefficient of variation of, in this case you can take diameter of breast height, or biomass also you can take. T is the statistical value of T at 95% confidence level, significance level, and AC is the standard error percentage. Here we take 10% error. Now using this formula, now this CV, the coefficient of variation, this will come from field, of course, because we will be doing a pilot survey. Without this pilot survey, we won't be able to calculate this. So generally in a small area, what we do around 10, 11 plots in different strata we lay, and then calculate the number of sample plots required. Now in this case, we calculate the number of sample plots of 26. Now same question comes, if the total number of sample plots required for the study is 26, where to lay these plots? Now here I showed you the area under each class. So what we'll do in the forest classes, will area proportional sampling will do. So in this case, if you see here, we'll distribute this 26 number of plots in different strata using this formula. Like the area, stratum, which is a bigger area, will have more number of sample plots. So it is area proportional sampling. Now once you lay out the sample plots, then you lay the plots, and from there you calculate, for the field data you will calculate biomass. Now then what you do, you relate this NDVI with the biomass. In this case it is actually it is biomass, growing stock. So this is basically this is growing stock. So you are relating NDVI with growing stock, and then in this case we got a good relationship between NDVI and growing stock. Similarly, NDVI biomass. Okay, so using this relationship, we can map the biomass of this area like this. So basically, if you see this equation, y equal to 640.5 x. Now this x is NDVI and y is your biomass. So here will be input will be your NDVI image, and you'll get the biomass image like this. Okay. Now this kind of methodology, or this kind of this thing, of course, this works nice, when you have when you are working with very small data sets, or maybe very low biomass content. So this kind of methodology or this kind of modeling approach will not work when your area has high biomass content. This kind of methodology is good for low biomass system. So here one dependent variable and one independent variable we have used. Now in next case, what I'll show is, so this is like what are the mean volume or total drawing stock, mean biomass and total biomass under each of this category, and in of course of the total area. Now here, what I want to highlight here is, now instead of simple linear regression, we are using multiple linear regression. Now in this case, what we are doing is, in earlier case we use only one variable from the satellite data derived variable. Now here we are using 11 variables, 11 satellite data derived variables, or you can say spectral bands as well as indices, and the field inventory, of course, this remains the same, since it is this area is a sal plantation area, so this is homogeneous. So we did only random sampling in this area. There is no there is all the areas are homogeneous plantation area. So here also you can see this is the satellite part, this is the satellite data, this is the field part, and then this is the modeling approach. There's three things. Now here is, in addition to simple linear regression, we also did multiple linear regression to map the spatial distribution of biomass. What we have observed here is that when we are taking only one variable at a time, one independent variable, one dependent variable, if you see the R square value is also less, but we are when we are taking combination of, let's say, 6 variables, this improves. Even the RMSE value also improves in this case. So it is better than simple linear regression. But again, these kind of approaches are not good when you are working in a high biomass content area. So moving further, so what we do basically when we have a high biomass area, so in these cases, there also we have used 6 variables only. In first case only, we actually used 11 variables. Out of this 11 variables, we have taken best 6 variables and did the modeling. Now moving further, what recently are being done is the machine learning approach, algorithms. So again, if you see here, this is the satellite, left part is the satellite data derived variables or satellite data parts, the right side is the field part, and then modeling part. Now here, what we have done is the number of variables that being used have been increased constantly. So this is band reflectance, then you have indices, then you have texture values also. So these are the number of variables that we are using now. And in field data, what we have done is we have sampled for trees, shrubs, herbs, and litter, and ultimately we got the total forest biomass. And then the modeling approaches, so the integration approach was neural network based modeling approach. Now in this case also, first of all, we did this forest type density map to stratify the area, so that we can go for a stratified random sampling, and we can distribute our sampler in different strata. Now again, to calculate the number of sample plots required for this study, we used a Charcos formula, which says T square multiplied by CV square divided by AC square. Now here again we have coefficient of variation. We did a pilot survey to get the value of the coefficient of variation. Here in this case also we have taken diameter at the side, biomass value also can be taken in that, and then ultimately we have distributed this number of sample plots in different stratum based on the area proportion. In this case we identified that there are 36 plots are required to study this. So where to lay these plots also we are clear now. Using this formula, we are stratifying this in different strata, and ultimately we know how many sample plots in each category. Now question comes, where we will be doing, what we will be doing in this sample plots. Now if you see this the sampling design, now this plot is basically used for 31.62 by 31.62 meter, which is 0.1 hectare size. This is used for trees. Then 5 meter by 5 meter, that each opposite corners, these are for shrubs, and there are 5 plots for 1 meter by 1 meter, 4 corners, and one at the center for herbs as well as litter. Now in for tree biomass calculation, what we do, we note in that 31.62 meter by 31.62 meter, we note down the species name, and then girth also. From girth we calculate the diameter. From diameter, using volumetric equation, we get the volume, and volume multiplied by the wood density, we get the biomass, and biomass, and around half, let's say around half of the biomass is carbon, or to be precisely, if we use the IPCC correction, this IPCC conversion factor is 0.47 of biomass is carbon stock. So, and for below ground biomass, these data sets are also, for getting this kind of below ground biomass reference data is also scarce. So it is estimated using a root shoot ratio. In certain cases, it is there in literature. So in our case, we have used a root shoot ratio of 0.3 for shoya robusta, and other species 0.26. Now, from this, we can calculate the below ground biomass as well. So tree biomass is in this thing, we can by this methodology we can calculate the total tree biomass, let's say. Now for shrub biomass, shrub biomass, what we do, we can of course we did 5 by 5 meter plots at the each corner, and we collect samples of each let's say species 1. There will be many species, so let us say we take species 1, and one sample is cut, and then they are weigh also. The fresh weight we take, and then we take a piece of this and oven dry also, and then we convert it to oven dry weight. Similarly for herbs, what we do, whatever we get in 1 by 1 meter plot, we weigh this. That means fresh weight is been taken, and then the a small sample of this is taken to the lab and oven dry it to get the equivalent dry weight. Ultimately, what we get this ultimately we get the oven dry weight of these shrubs as well as herbs and liters as well. And combining this, we can get the total biomass of this. So these are the 36 plots that we laid in that area, and then these are tree biomass, then below ground biomass, and then like herbs, shrubs, and liters all. So we get the total biomass in each of these plot. Now this is the strata wise the biomass in different strata. If we take a different strata like salivary and salmoretless, so you can say tree biomass, then mean tree biomass, then above ground biomass, mean below ground biomass, shrub, herbs, litter, and total biomass also. So this is plot wise, this is again strata wise. Now here, so these are the points. So what we need to do, these points are so in this case what I showed earlier also, these are the field biomass how we calculate, and then what you do, you use these variables. So if you see in this case, these are the independent variables you are taking. You are relating this with the biomass. So this is the dependent variable, and this part is the independent variable. And in this case, we have used neural network based modeling, and we could map the biomass of this area like this. Okay. Now moving there is one more method of machine learning approach which is very popularly being used all over the world, and this is very effective. This is called random forest algorithm. This is if you see the literature, recent literature also, this algorithm is being effectively used for forest biomass mapping. Now here in this case, what we have done is, again, if you see, this is the satellite data part, this is the field inventory part, and this is the modeling part. So in this case, we have taken spectral variables as well as texture variables. So these are the independent variables, and then these variables were related with the above ground biomass, that is field biomass, and integrated this with the using machine learning algorithm, that is random forest. Here what we have done, we have independently we have seen, like we have taken spectral variables at one time and related with biomass, then texture variables with biomass, and then combination of spectral and texture variables and related with the biomass. And what we have found in this case is which is the best model And after getting the best model, we have tried to identify the best predator variable. Now in this case also it is not advised that suppose you are using 130 or 150 very independent variables. It is also not advised like you know recommend somebody to use 150 or 130 variables to do modeling. So you need to optimize this predator variables. That means out of a set of let's say 130 140 variables, you take the best 5 or best 6 or best top variables and then predict biomass and see what is the accuracy level of this. Now using this approach you could effectively map the biomass of this special above ground biomass of this area. And nowadays earlier we used to provide these R square values and the RMSE value. Now these this thing like R square and RMSE value this will give an idea of what's the accuracy level of your map, but you are not sure whether the accuracy is distributed all over your area as same or different. So to get a better idea of how accurate my biomass map, we need to generate the uncertainty map also. This is uncertainty map of this. Now here where the accuracy of your map is more, where accuracy is less. Only giving numbers is now not enough. You need to provide an uncertainty map wherein you can identify the spatial distribution or error, where error is more, where error is less. Because if somebody wants to use your map, he should be able to understand like where modeling was correct and where modeling was not so good or modeling output. So here we have what we have observed that machine learning approaches like random forest and artificial neural network. These are the better approaches for assessment of biomass. For this, you need to have more field data, and more number of variables also need to be taken care of. And out of the set, as I said, out of a set of let's say 150 variables, it takes the best predator variables and let's say 6 or 7 variables and predict the biomass with quite good high accuracy. So this is this approach is very effective when we are using a moderate resolution satellite data. Moving further to high resolution satellite data. Now when I'm talking of very high resolution satellite data, that means I'm talking of let's say 0.5 meter resolution kind of or less than 1 meter resolution. Now in this case what we are what I'll show you is now how biomass or carbon can be assessed using a very high resolution satellite data. Now when you have a very high resolution satellite data, your object is visible in a very high resolution satellite data. I'm talking of less than 1 meter spatial resolution like World View 2, Cartosat 2S, Cartosat 3, like that. So when your object is visible, that means your modeling in this case will be slightly different than what you do in medium resolution satellite data. Now here what we do basically, now if you see here, now we in field this is called canopy projection area, which is shown here. So by developing a relationship between canopy projection area and diameter of a species at site, so it is species specific and site specific, we generate an equation. So basically, because from satellite data we cannot map the diameter, so what we do, we map the canopy projection area, and there exists a relationship between canopy projection area and diameter of a species at specific sites. So by developing a relationship between these and canopy projection area and diameter, we convert this canopy projection area into canopy projection area map into diameter map, and diameter to then using volumetric equation we convert to volume to biomass to carbon. That means you are able to delineate or map the individual tree carbon. Now coming to this, what we do generally, there are two steps basically for satellite data processing. Major step is image segmentation. First of all, you do segmentation of the image, and then you classify the image. You separate trees from other, and if possible, can we identify different types of trees? It depends on the complexity of the area as well. And from the field by developing a relationship between ground projection area and the carbon. We get the carbon stock map of the area. So here in this case, if you see this map was, this is the map generated using a relationship between carbon and ground projection area. So by generating this, we can using this kind of relationship, which is depicted here also. So here X means CPA. So using this kind of relationship, we can generate these maps. And a zoomed view of this is here. Now, if you see this, each of the segments, these are individual tree crowns. So here I'm able to map individual trees, and at the same time I'm also able to map the individual tree level biomass. So this kind of modeling is slightly different than what we do using medium resolution satellite data. Now coming to the active remote sensing, here in active remote sensing I'll be specifically discussing on the lidar remote sensing. Now lidar basically is light detection and ranging. It uses laser pulses to detect or determine the range of object or height of object also. When it is used for determining height of any target, it is called laser ultimately, or you can say lidar. Okay. Lasers are basically is a device that emits electromagnetic radiation through stimulated emission in which narrow wavelength of channels are emitted. Now, in how it works, so basically what we do is you send a laser pulse toward a target. So in our case, the target could be a tree. So you send laser pulses. Let us say in this case, you are sending laser pulses from an aircraft. And these the laser pulses are hitting the trees like this and going back. Okay, so and in this case, one thing care should be taken that some of the points should reach ground. If the points no points reach ground, you won't be able to get the height of the trees or the reference. If you don't have the reference, you won't be able to get the calculate the height of the trees. So basically, you send a laser pulse towards the target, and and measure the timing and the amount of energy that is scattered back from the target. The return signal timing provides a measurement of the distance between the instrument and the object. Now, like D is equal to D is the distance between instrument and the sensor and the object, and C is the speed of light, and T is the time taken for the pulse to return this T. Now by this, if I can get the distance from here to here, I can get the distance from here to here as well. So using this, I can calculate the height of the trees. But in this case, care should be taken that some of the pulse should reach the ground or the reference. Otherwise, if everything goes from up, we can get the distance only, but we won't be able to get the height of these trees. Now, by platform, we can say there are three kinds of lidars, like terrestrial lidar, airborne lidar, and space-borne lidar. So I'll discuss one by one. Let us start with, let's say, terrestrial laser. Now, terrestrial laser basically a ground-based laser instrument. Now, here you have a laser instrument, and it is basically used to for getting accurate tree structure. So it can be used for at tree level or plot level. Okay, so detailed information of the tree or plot, it gives this kind of information. Now, how operate in a forest area? Now, let us say, suppose we are in a forest area like this. What we do? Now, when you are in a forest area, you are surrounded by trees. So anywhere you are standing, you are surrounded by trees only. So what do we do? Basically, we mark a plot and mark the corner trees with the reflectors, so that we can identify. After scanning, we can identify like this is the area, or this is the plot, sample plot I am talking of. And this instrument was used. This is VZ 400, real VZ 400. instrument, and this is the scanner. So basically it scans from this, and it scans like this. So the vertical angle here is 30 to 130 degree, and the horizontal angle it can move 360 degree. If you move like this, it can move 360 degree, but vertical angle is 30 to 130 degree. And there is a camera also attached to that. So I'll discuss about the camera also in next slide. So how do we scan? So basically we put this scanner at the center of the plot, and these are the red ones. The red circular things are called circular reflectors. Okay. These act as actually tie points. These are rectangular reflectors or circular reflectors. These act as tie points when you do scan from different positions, or there are 2-3 scans, and then you using this you merge this data using this kind of tie points. Now, suppose we are scanning from center. So as I said, the horizontal angle here is 360 degree, so we can get a whole scan of this area, and the range of this instrument is 600 meters, so we can scan outside as well. But our area of interest only this, so will be because that's why you have put reflectors, so that we can understand only at a flat level. But problem is when we are scanning from, let's say, here, so this tree is behind the front tree, so I won't be able to get any information about this tree. Similarly, it will happen with others also. Now, how to get this? And moreover, if and then this horizontal vertical angle is 30 to 130 degree. So the trees which are near the instrument, you won't get the top of these trees, because suppose one tree is here, you won't be able to see the top of the tree, so you won't get the information. So for this, what we do, we scan from outside as well, like this, like this. The position of this, scanning from outside the plot depends on, what's the density, position, and the number of scans also. If the area is very dense, you may need to have one more scan from this side as well. So what we do is we place in the scan in such area that from this we can see the maximum number of trees, like this. So from here also we scan like this. Now here you don't have to go for 360 degree, because I don't need information about from behind this thing. Okay, so I only need information about this. This can be fixed also. So here I can scan like this area. So here we have this center position, then you have scan number 1, scan number 2, and scan number 3. Once this is done, what we do is you merge all these 4 scans to get a 3D model of the forest. Now this is actual scenario in field, how we do. So these are the, as I said, these are the corner reflectors. These are the corner reflectors that put in the tree. These are circular reflectors. These are used for, these act as a tie point. So when you merge scan 1 with scan 2, this will act as a tie point. Similarly for scan 2 to scan 3, because, and one more thing care should be taken, that this should not be moved at all when you are scanning from different angles, different positions. Only thing, the surface, this surface should be towards the scanner. Now there is a when you are scanning from outside, of course, you can scan from around 5 to 10 meters. That depends again on the density of the forest. And the vertical angle, you can, the horizontal, when you are scanning from outside, the horizontal angle can vary according to the situation. Suppose you are scanning from here, the angle will be, let us say I'm scanning from here. So instead of 0 to 360 degree, I can scan this angle only. So this can be fixed. And then there is a camera also attached to this above this scanner. So once your scanning is complete, it takes photographs of this area. Overlap of the photograph you can decide. You can keep it 50% overlap or 60% overlap. The images, these are used to colorize the point cloud only for better visualization during processing. So these are because these are non-imaging, so you get point clouds only. So what we do, using these photographs, you just take the color from these photographs to colorize your point cloud data so that you get a real 3D kind of your area. Now this is how a data looks like. Now here you see this is the scanning position from, let's say, center. So when you do scanning, you won't get any information below this. This is a occlusion effect. And suppose this tree is there behind, whatever is there behind this tree, you won't also get. So that's why we get scan from different positions. And then again, this is from scan from different positions. Then we merge this to get this kind of thing. Like this is a merge point cloud of center position, position 1, position 2, position 3, all four. So once we see this, the 3D, it gives a 3D model of the forest. So it looks like this. So you can see, after merging this, all this, you can visualize your area like this. So you can get a 3D model of the forest. Now, what are the parameters that can be retrieved from this kind of data? So again, this is not a photograph. This is a 3D model of the forest. And as earlier also I said, like the photographs, the color from the photographs are taken to colorize the 3D point cloud like this, and we got a result like this. So this is the real picture, it seems to be a photograph only, but if you expand this, you can get point clouds all over the places. Now, what are the parameters that you can derive from this? So here, from the plot level, we distinguish different trees, and then a single trees were extracted out, and then you can also remove everything from the ground, everything from the surface, and you can get these white dots are basically the position of the trees, and then you get the height of the trees in meter and diameter in centimeter. This is a teak tree, almost leafless, so you can see the skeleton structure of the tree, and you can count the number of branches. You can do measurement at any point of time without basically you are not cutting the tree, but you are able to get all this information about detailed information about the tree. So basically what we get is position of the tree, diameter of a tree, height of a tree, and canopy projection area also are being derived. Now, in addition to that, when you can do vertical stratification of the forest as well. Now, suppose this is my overall point cloud data or the 3D model of the forest. I can separate this into terrain part. Then I can say this is the ground vegetation. Then these are the small trees, and these are the tall trees. So if my study requires stratification kind of thing, so these kind of data can be very effectively used. So based on the height, you can separate all the layers, and you can effectively use this kind of data for your study. What we have observed that in the field, we have compared the diameter, height, and CPA that is measured, that is derived from the TLS data. This compared the field data, and we have observed very high accuracy. It gives very high accuracy in all the cases, be it the diameter or height or canopy area. Similarly, what we have done is using this kind of inventory parameters from the terrestrial laser scanner, we have derived inventory parameters, and we have calculated biomass. And integrating this with the satellite data, we could map the biomass of this area also. So in this case, we have done field inventory using terrestrial laser scanner. Now, this kind of maps can be generated using so a biomass map as well as carbon map of the area can be generated. So basic application, if it's the main application of this or terrestrial laser scanner is getting the plot level forest inventory information like diameter, breast height, tree height, stem density, basal area, this kind of thing. Vertical forest stratification is also needed, and one of the most promising scope could be generation of species as well as site-specific volumetry equation. So these can be utilized very effectively for generating for when we are studying at tree level, or at the plot level. So detailed information about the tree structure and plot level information also can be studied using terrestrial laser scanner. Coming to the next platform, that is Airborne lidar. So by the name it is, we are using that aircraft. In this case, aircraft is the platform, and here we have of course there will be a laser scanner. There are GPS also in that, and there is one more thing called IMU, or the inertial measurement unit. So it gives a precise orientation of the scanner, because when the flight moves, there are movements in all the XYZ direction, which is called roll, pitch, yaw. So to correct these, you need this kind of correcting measurements. So IMU, this inertial measurement unit, is there, which gives correction due to this movement. So how this data looks like? So suppose this is a tree, and you will send laser pulses from the aircraft. It will touch different parts of the tree. Now the number of points, or the density per unit area or per meter square, you have to decide prior to your planning, flight planning. So when you are planning for flight, this airborne data acquisition, you should mention like how many points you need per unit area or per meter square. So in this case, let's see. So this is the tree, and you are sent laser pulses. So it is, and if I get the data, it looks like this. So it gets the complete structure of a forest. Now using airborne data, you can cover a larger area. It's not like at tree level or at a small plot level. You can cover a larger area, and very accurate measurements also it gives height and structure. Now this is actual data of a forest area. Now this is a part. This area is is a part of Nepal, and there are areas also Nepal. And this, if I see, this is the zone part of this. This gives the vertical forest profile. Now here you can see the height information of this thing. Now here I can get the vertical distribution or vertical forest profile of the forest. Now using this data set, I can generate the DSM, or digital surface model. I can remove everything from the surface to get the DTM, and when DTM is subtracted from the DSM, I can the canopy height model, or the So basically here I'm talking of, we can see here the DSM, then DTM is the digital terrain model, and then canopy height model is the CHM. Now in forestry we are more interested in the canopy height model. So basically, if you see here, this is the actual data. So here we get the everything in the surface, or surface model, digital surface model, and we can remove everything from the surface to get this thing. But if I subtract this DTM from the DSM, I get the canopy height model. So a zoom part of this is shown here. Now if I click any of these points, I'll be able to get the height information. Now the question comes, when we do biomass estimation using a optical data, we are thinking is a 2D kind of information. We are not including 3D or the structure information as such. So in this study, what we have done is we have incorporated the structure information as well. So in addition to your optical data, we have used lidar data as well to get that structure information, and we have found out, like, if we use only lidar, if you use only optical data, does it give better accuracy? Or if we get a combination of lidar and optical data, it gets more accuracy. So what we have found is, when we have combined or integrate, we are integrating lidar with optical data, the accuracy of biomass estimation is more. So in this case, you can see here we have done different kind of modeling here. Now in this case, we have first tried with only spectral variables. Now in this case also, biomass is the dependent variables. All these are independent variables. The spectral variables, then only texture variables, and only lidar variables. Then we have combined spectral and texture, spectral and lidar, all possible combination, and ultimately with spectral, texture, and lidar. So basically optical and lidar. And we have found that the RMSE in this, when I'm combining this all, we are getting a better estimation of accuracy. So it highlights that single sensor approach is not good enough to study biomass. multi-sensor integration approach is better. It gives better accuracy of biomass estimation. Now here we could using this combining lidar as well as optical radar variables, we could predict biomass very effectively in this area. So airborne lidar, of course, free height. When I'm talking of lidar, of course, height and forest structure. These are the most important variable the most important variable that we can, derive from this data for getting the, for constructing the 3D forest structure. In addition to that, you can do using this kind of data. Wherever you need height information or height modeling as an input to any of your study, whether it's a wildlife suitability modeling study or any other study, you can utilize this kind of data very effectively. But overall, these data sets are used mainly for studying biomass in forestry, biomass and carbon assessment with high accuracy. Moving further to the next platform, that is the Space-borne lidar platform. So recently there are two missions. One is a global ecosystem dynamics investigation, or the JEDI. Another is ISAT-2. ISAT is Ice, Cloud and Land Elevation Satellite. ISAT, there is one more satellite like ISAT. It worked from 2003 to 2009. But there are nothing from 9 to 18. So recently there are two missions. There are two lidar missions, and there are two lidar missions, and they are capable of estimation of forest canopy structure and biomass, JEDI and ISAT-2. Now, first of all, I'll discuss about the ISAT-2 and how this can be utilized for forest biomass carbon assessment. Now, then ISAT-2, this is launched in September 18. And from 14 October 2018, we are getting the data. It is an instrument called Atlas, Advanced Topographic Laser Altimeter System, and it works in the 532 nanometer. And it has 6 beams of 3 pairs. So, and footprint is around 11 to 14 meter footprint. So, if you see the data set, it will have 6 beams and 3 pairs, and there are strong beams as well as weak beams as well. So when you study for other low reflectivity targets like forest, we should take only the strong beams. We should not consider the weak beams for this kind of study. So in forest study, we generally take the strong beams. So in this pair of 3, we'll have strong beams as well as weak beams. So first of all, we need to separate the strong beams from the weak beams, and the strong beams are being used further. Nowadays we are getting the product basically of so for forestry purpose we use this product ATL08. So it gives height information directly. ATL03 is also being used, but mostly this ATL08 is used. Now if you see here, like these are the I'll talk about where can you get the data. So these are freely available data sets which you can access through Open Altimetry website. So go to this browse ISAT-2 data. In Open Altimetry, you go to browse ISAT-2 data, and it will have this kind of so you'll get a global coverage. So you zoom into your area, so you can see this 6 beams or 3 pairs, as I earlier also said. So you'll have strong beams as well as weak beams. Now, if you zoom into any of these areas, you will get this information. You can and if I select any of these points, I can get directly the surface elevation as well as the canopy height information. So in this case, you can see over this area, the highlighted area, it can give the canopy height profile. Now, what recently we have done a study. This is the first study using ISAT-2 data in Indian forest, wherein we integrated ISAT-2 data with other data set to get to map the forest height as well as biomass. Now, if you see here the methodology, so basically from the ISAT-2 data, which gives the height information, this was integrated with Sentinel data derived variables like backscatter and texture information, and using a random forest based modeling, we could get the forest height information or forest height map. Now integrating this forest height map in biomass estimation now. So what we have done, this is the field inventory data. So from this we are getting the biomass, evaporated biomass. This is the dependent variable, and from Sentinel-2 we took the spectral indices or the spectral information, and integrating these two we got the using again random forest space modeling, we got the biomass. But here we have tried is inclusion of height data in modeling or height layer in modeling. Does it get better estimation of biomass, or what we are doing earlier using integrating, let's say, medium resolution satellite data, variables and field data, we are satisfied with that. So this was tried, and it was found that when we integrate canopy height information in addition to spectral information, we get better estimation of biomass compared to when we only use spectral information. So like this we could map the forest canopy height. So this is a 3D view of the forest canopy height. What we have done is point locations. So in ISRO data or the space-borne data, we won't get wall-to-wall lidar points like what we get in airborne data. So here you can see we are integrating this lidar height data with the sentinel data to get this kind of maps of the height map, and then integrating this height map along with the spectral variables. So there are spectral variables as well as height. So spectral variables and the height, these are independent variables, and the biomass is the dependent variable. So dependent variable. So integrating this using a random forest based model or the machine learning based model, it gives the best accuracy compared to when we are trying with the single either just optical or the lidar one. This study also highlights that the sensor integration or multi-sensor approach is better than single sensor approach when we are studying biomass. Similarly, the other satellite, which is other data, is JEDI, the Global Ecosystem Dynamics Investigation. Now, this is on board to International Space Station, and this is also launched in 2018. Here, this is waveform kind of data, and the footprint here is 25 meter. This data set is again very good information for carbon stock assessment as well as net carbon stock due to disturbance and recovery in a forest. You can assess that net carbon also. So in this data there are 8 ground tracks and 4 beams, and footprint size is around 25 meter. So this kind of data can be very effectively used for because there is repetition also. So you can get the tree growth, you can study the tree growth, you can study mortality, you can study regeneration, you can study competition as well. Now the various questions that we generally come across, like can we get the carbon balance of our forest? Yes, this can be addressed through this kind of methodology by quantifying forest biomass and also studying the disturbance recovery, and using this carbon sequestration, studying the carbon sequestration potential, we can able to give answers to how will the land surface mitigate atmospheric CO2 in the future. Vertical forest structure and its response to biodiversity also can be quantified using this kind of data. So basically, what we are doing, we are extrapolating this local information and local measurement at one footprint. These we are integrating with the other data sets to get a landscape level data or over a larger area, and these are ultimately used for assessment, monitoring, and decision making purposes. We also have done a study using this JEDI data by integrating JEDI Sentinel-1 and Sentinel-2 in a hilly area of Podiga rural district of Uttarakhand. There also we have found that these kind of data sets, when I'm integrating JEDI with Sentinel-1 data set, I can get very accurate high biomass, accurate forest canopy height map. And when I'm integrating forest canopy height information along with the spectral information, I am getting the best development biomass content as well. So there is one publication by Kotava in 2021. After this, there is one more also, but there they have generated global forest canopy height map. The grid wise this can be downloadable, and you can try in your area also whether the canopy height map which is being generated, how accurate is this. Sorry. So space-borne lidar, as you have highlighted that, it can be very effectively used for forest biomass, carbon assessment, and disturbance recovery, and also studies related to vertical distribution of vegetation. And in addition to that, you can also use this for, let's say, habitat suitability study. What studies? Simply studies which are related to structure of the forest. Okay, but the main focus of this kind of data is forest height, biomass, carbon sequestration, disturbance, and recovery studies. So to conclude, must say that as we know that forest plays a very important role in carbon cycle, hence monitoring, mapping, as well as monitoring of forest carbon. These are these should be done very effectively, and remote sensing plays a very important role here, because remote sensing, integrating field inventory data with the satellite data, we can very effectively map the biomass. So it's not only only remote sensing or only field data. There's the integration of field data and biomass to get the very effectively we can map and monitor the forest carbon stock in this area. And with the recent advances in the field of remote sensing and informatics, like availability of new sensors in both passive as well as active domain, improved resolutions, be it spatial or spectral or radiometric or temporal. Advanced algorithm is not only the available data, the method or the approach by which you integrate these two, there are also modifications needed. So by uh, getting this kind of information, or the availability of this kind of data integration methods, like machine learning and all, this is more giving more advantages over the previously used methods. And use of cloud platforms like Google Earth Engine and different data handling techniques to help large data sets. So availability of all these, these are your these are used. This can be used actually for better estimation of biomass, and not only mapping, also monitoring of the biomass. And so I can, to conclude, I can say that all these, availability of data, availability of algorithm, availability of platform, this can lead to fine scale mapping and monitoring of the forest biomass carbon. Thank you all.